Hello, I'm Nan, a graduate student at Christ AI. I'll give you a short presentation on the research I've done while working as an intern at Keats. To restore sight to blind individuals, several visual processes have been commercialized or are under clinical trials. Those prosthetic systems elicit artificial visual percepts through an array of bright white dots, so-called phosphenes, in various sizes and grayscales depending on stimulation parameters. To answer how to effectively present our complex visual images using a limited number of pixels or phosphenes conventionally, human psychophysical tests have been conducted. For example, they showed various faces in the original resolution first and the phosphenes on the next screen to determine the minimum resolution of pixelated artificial vision for various faces to be distinguished. However, these human psychophysical tests are generally considerably time-consuming and costly. Any minor tweaks in the phosphene image processing algorithm may require another set of psychophysical tests. Motivated by recent studies that compare the performances of humans and machines in high-resolution synthetic images and distorted images, we explored whether the machine learning model is an effective alternative to human psychophysical tests. However, it has been known that the learning effect exists throughout the experimental trials and human psychophysical tests. Even when the task is challenging, the repeated behaviors of humans could increase their performances. Hence, we opted for a reinforcement learning algorithm to mimic human behaviors in the psychophysical test faithfully. With the proposed framework, we aim to connect the field of artificial vision and the reinforcement learning method. Here, an initial agent interacts with our customized control environment called the bionic eye environment, which contains answers previously selected by 9 training human subjects. We define the state as the sequential phosphene images presented in the human psychophysical test. They are fed to the agent or convolutional neural network, and the agent or network chooses the action of selecting the target facial image. If they choose the right facial image that aligns with the human's choice, the environment gives a reward of 1 and 0 for otherwise. Our feedback framework consists of 2 phases, training and automating. Here is a pseudocode for the training stage. We first initialize the parameters data for the Q network, or phi and theta for the value and policy network respectively. Also, we set replay memory buffer D, which will store the transitions of experiences, state, action, reward, and the next state for the agent with the maximum capacity of N. The next step was optional, where the Q network or the policy network was pre-trained for E sub P epochs using 1K high-resolution images per facial class to start the actual training with more optimized parameters. For each episode E from a total of large E episodes, the first state S sub 0 was always the first specific low-resolution phosphene image shown in the human experiment. Then, the agent experienced all T-1 states in which the parameters were chosen from the resolution levels of 16 by 16, 32 by 32, and 64 by 64 pixels, and the grayscale levels of 2, 4, and 8. In the third for loop of algorithm 1, the action and reward were chosen based on the conditions described in the previous slide. The agents in DQN and DDQN used the epsilon greedy method to explore the environment with a probability phi or exploit Q network otherwise. Since the order of experimental trials was unchanged throughout the human psychophysical test, for all subjects, the next state, S sub T plus 1, was independent of the selected action. All the transitions up to T were saved in the memory buffer, but also discarded with the first in first out method if the buffer size exceeded the maximum capacity, and the current state value was updated for the next trial. If the replay memory size became greater than or equal to N, the parameterized networks were optimized with random transitions. As more experiences were added to the buffer, the number of samples entering the Q networks also increased. However, the buffer was reset after each episode for PPO, since it did not need older data to train this algorithm. The Q network or the policy network updated after all trials per episode was saved for later use in the automating part. Then, in the automation stage, we collect test accuracy per trial using a fixed Q network or policy network per episode. More specifically, using the trained network, we generated several human-like agents to emulate human perceptual changes over time. We first divide the saved performances for each experimental trial and episode, except for the first few initial episodes. Then, we randomly selected multiple agents of which the number corresponded to the number of human subjects from the divided section. Finally, the performances were averaged over M agents for each session and concatenated to attain the final non-stationary evaluation accuracy. First, we found that the pre-trained DDQN is the superior. First, we found that pre-trained DDQN is the superior RL algorithm from the training phase of the feedback framework. This was empirically proven by comparing the training curves that track the average reward over 1K episodes for DQN, DDQN, PPO, and their pre-trained versions. First, pre-trained models achieve much higher performances throughout the episodes compared to the non-pre-trained versions. Second, DDQN showed slightly higher performances than DQN, and especially in their earlier episodes. Because pre-trained PPO could not be properly trained because of the gradient explosion problem, we presented the results of two PPOs trained with learning rates of 20-5 and 5e-5, at which the learning curves were much more slowly saturated compared to DQN and DDQN. Hence, we selected the pre-trained DDQN as the best RL algorithm to create artificial agents in the automating stage due to the fastest convergence with the highest reward received in the last training episodes. Here we show that the artificial agents produced in the automating stage of the best reinforcement learning framework could emulate the learning effects of humans. Here, 9 artificial agents were generated using pre-trained DDQN to imitate the facial recognition performances of 9 human subjects, whose behavior performances were unseen by the agent in the training process. In other words, 18 human subjects were separated into training and test subjects, and we only used the behavioral information of training subjects for making the feedback framework. As you can see here in columns A and B, the agents could show largely similar average performances of the subjects. The overall facial recognition accuracy of artificial agents were much higher FRAs than those of the supervised learning model with the same neural network architecture bionic environment in the reinforcement learning algorithm. Because the increased tendency of the accuracy was not monotonic in general, we used these two metrics to compare 3 models. Although all this showed a positive gain based on the first metric, delta FRA max, only the human subjects and the artificial agents showed more than or equal to 10% for the second metric, delta FRA AN. The pre-trained DDQN artificial agents and the humans generally showed similar behavioral changes for each resolution as well. For 2 out of 3 resolution levels, each of the 9 agents generated using the pre-trained DDQN showed a higher resemblance with human subjects than SL models. In detail, Pearson's R values were much higher for the agents and the human subjects compared to the SL models and the humans. Furthermore, although both the agents and the SL models saturated with an accuracy of less than 40% in set 1 for the resolution level of 16x16, only the agents could improve their performances over the following sets, unlike the SL models. For the higher level of pixel counts, the agents were much more accurate at the first set than the SL models, approximating that of the humans. In addition, to unravel how the Q network is trained throughout the episodes, we investigate how the sample processing images with a resolution level of 16 by 16 with 4 grayscale levels is filtered for each layer of the network. As you can see here in the untrained Q network, the original low-resolution phosphene images were shown frequently in all of the filters. The sample filtered images from the first and third compilational layers placed on the top row inside the yellow and purple squares, respectively. However, as the network was being trained for more and more episodes, in contrast to the filtered images started to However, as the network was being trained for more and more episodes, the contrast of the filtered images started to decrease, implying that the agents were getting used to learning the abstract forms of humans. This suggests that the agents learned to recognize the faces in low resolutions better over time, proportionally to the number of training episodes and average rewards, mimicking the short-term learning effect of human subjects from the psychophysical tests of artificial vision. Thank you for listening. If you have any questions regarding our work, please send messages through one of these emails.